So my talk's going to be a little bit different than what we heard earlier today. I'm going to be focusing on sort of more of the ingredients and the hardware components that enable a lot of these systems and databases. A little background on what I do. A couple years ago, Intel started looking a lot more at the entire solution space as opposed to just providing different ingredients and letting the marketplace or the ecosystem develop them. We realized that as the components are becoming more and more complicated and there's more choice and there's more complexity as to how you put these things together, we have to take an active role in terms of providing guidance, benchmarking. And so there is a team within the enterprise and government organization that deals with building solutions. And by solutions, these are essentially reference designs that help an end user, helps an OEM, an ISV, an SI to figure out how to take all these different components together and build something that is high performance and low cost. So I'll just touch briefly on this. These are sort of the three big areas that we focus on: cloud, comms, and enterprise and government. The last one is the org that I work for. Enterprise and government works with pretty much lots of different customers and lots of systems that are on-prem, and hence there is a very strong need to understand how different components can be put together and used in different ways, from fairly small systems in a small enterprise to some of the very large HPC deployments out there. So yesterday was actually a very big day at Intel. There was a mega launch for a whole number of products out there. So I'm glad that I could talk today and not yesterday, because yesterday I would not have been able to say half the things that are in the slide deck. But there are quite a few components. We'd look into the connectivity space. There's more and more products into the storage space. And of course, on the compute side, there are quite a few things going on. There are specialized products coming up in the AI space. This is a network process. This is a neural network processor. This is an edge AI device, as well as FPGAs that are coming out. I'll talk a bit more about these later. Just wanted to highlight here. This is a relatively new program that Intel has called Intel Select. The goal is to take this soup of ingredients and sort of put them together in a set of reference designs. This is the projects that I typically work with. So here's a sampling of the sort of portfolio of solutions that we have available. A number of these are new. For example, there's an AI inferencing solution that's coming out this week, actually, and there's also an HPC AI converged solution. But pretty much we try to look at all the sort of different segments and try to understand what are the end customer needs and what are the reasonable configurations, both from a hardware perspective as well as a software perspective of how to put these things together. So, announcement yesterday. I'm not going to give you the details for all of these, but we have a new set of processors that is out. Code name was Cascade Lake. You might be familiar with that, but they're basically called second generation Xeon Scalable processors. All of these over here are updates or refreshes on previous generation of processors. This one here is new. The high-end Platinum basically consists of taking two dies and putting them together, so the socket itself has about twice the number of cores. So we can get a two-socket system ends up having more than 100 cores. This is the full chart of the CPUs that were released yesterday. I'm not going to go through them again. But just want to highlight a few things. As you can see, we have these very high core count CPUs. This is new. This is not something that was available until yesterday. The idea is we can build higher density systems. So the same form factor can have twice the number of cores. Of course, you end up having quite a bit more power as well. There are also a few interesting new additions. For example, there is a set of CPUs that has something called speed select technology. What does this mean? If you're familiar with the way that turbo works in CPU, there is a guaranteed frequency, and then there is a maximum frequency depending on the workload. The guaranteed frequency is the minimum frequency that you operate, and when you need it, the frequency will go up and down. What speed select allows you to do is you can change the guaranteed frequency on a per core basis. So you can say I have 48 cores, and 10 of these cores will have a higher frequency. The other ones will have a lower frequency. That gives me the ability to pin applications that require that higher frequency to the cores that have that. So I have different guaranteed frequencies for different cores. There are also specialized cores for specialized CPUs for networking, as well as for VM density, for long life cycle, and even for search. This is our flagship CPU. It has up to 112 cores on a 2-socket system. It has twice the amount of compute density in terms of cores, higher frequency than was available in the previous generation, and up to 3 terabytes of DRAM. The DRAM also it's being pushed further in terms of frequency. We're getting close to the 2933 mega transactions per second. And then if we're looking at how to scale these things beyond single socket or 2-socket systems, we have the high-end CPUs have the ability to get into 8 sockets or above. On an 8-socket system, we can turbo it up to 4.4 gigahertz. There is also an increase in the amount of system memory, and this has to do with some persistent memory as well. So when combining regular DRAM with persistent memory, we may have systems that have up to 36 terabytes of DRAM, which is something that was not doable just one generation ago. And similarly, we have the same kind of very high-speed DRAM. All right, in terms of features, there are a few things that we'd like to mention, new features that are being available. One is the Intel OPTANE DC persistent memory. I have some slides afterwards to talk about what that does. It comes with data encryption, so the data can be encrypted while it's in memory, not something that you can do with regular DRAM. There are a number of mitigations as well for side channel methods. This obviously was a big issue of the last 2 years or so. There are, this is the speed select technology that I was mentioning. You can configure the core frequency differently on a per core basis. There is another interesting feature called Deep Learning Boost. The technical name for this is VNNI. It's basically a instruction set, a new instruction set that allows us to do AI inferencing faster, and I'll talk a bit about that later. There are also some new SSDs and some new higher speed Ethernet with hardware queues in there. I will go through most of these in a bit more detail later on. Ethernet as well. We announced yesterday the 100 gigabit Ethernet card. This is 800 series. Not only is it faster, but it also supports a number of hardware acceleration within the card, like application device queues. So a number of functions that were typically done in software in the past can be accelerated in the actual hardware. And FPGA, this was also announced yesterday. This is the first FPGA that is made by Intel. As you know, Altera was acquired by Intel a few years ago, and Altera had a portfolio of FPGAs, and those have been rebranded and sold by Intel. This is actually the first product that was built as a product of that merger and not preceding the merger. Just wanted to highlight one key area here, which is this, the fact that it can be cache coherent with the Intel Xeon. So it's a very different paradigm from the past where you had an FPGA as a co-processor, as an accelerator living on the side. This is designed to work side by side with the CPU. So just like a CPU has access to DRAM and memory, this has access to DRAM and memory. It has access to persistent memory as well, just like any CPU, and it talks to the CPU through a cache coherent protocol. Right? So either UPI or a new bus called, I think, CLX that is coming out. The beauty of this, of course, is that you don't have to transfer data from an FPGA to a CPU. It can be in the same memory subsystem, actually in the same cache. Right? So if you have your CPU doing operations on the cache, the FPGA can use the same cache and use that. There's no transfer of memory. Right? There's also no conflicts about who has the right copy and so on. It's just everything's in the same memory subsystem, and both FPGA and CPU have access to that memory at the same time. All right, so this is what I want to spend a little bit more time on. I think it's a bit more relevant towards storage and databases. So this is a technical code name for this was Apache Pass. The marketing brand is Intel OPTANE DC Persistent Memory. It's a bit long, but basically the idea came with what happens if I take 3D crosspoint technology to build something that looks like DRAM. It's as fast as, or almost as fast as DRAM. Same bandwidth, maybe lower latency, but has the same types of characteristics of persistent storage. Right? It's not volatile. It's much cheaper, and it has much bigger size. Right? And this is where persistent memory came out. It comes in the same form factor, same DIMM form factor as DRAM. It's replaceable. You can populate a DIMM slot with either old-fashioned DRAM or with new persistent memory, but it allows you to come up with much larger configurations. I think today the largest DDR4 DIMM you can buy is a 128 gigabytes for one of these. These start at 128 gigabytes to go to 256, 512. So you can build much bigger system memory, much bigger memory footprints for a system than you could with traditional DRAM. This I think is a picture that kind of gives you the overall chart. We typically look at storage or the memory hierarchy as three pieces: as DRAM. Well, it used to be two: DRAM and then storage, and then hard drives. With SSDs coming into the picture, created a kind of the middle layer as well. With OPTANE, we're adding essentially two more layers. So we have a pyramid now of 5 different layers, and maybe you could say hard drives and tape are also different as well. but you have the ability to go really fast, low latency for DRAM. If you don't care so much about the low latency, but you want the higher memory capacity, you can go with this. If you want something that looks like storage, but is much faster than a regular SSD, than an SSD, there is OPTANE SSDs. If you want something that's cheaper and bigger capacity, you go here, and likewise for hard drives. This obviously makes things a lot more complicated because now you're not just saying, well, I can pay $10 for DRAM, I can pay $1 for SSD, or 10 cents for a hard drive. There are many more variables, right? And even within each of these spaces, you also have a spectrum of performance versus cost. And how do you build systems, operating systems, and programs and applications that take advantage of this is non-trivial. So a lot of the work that is being done in my team is trying to figure out ways in which we can take existing applications and make them faster by taking advantage of this new memory hierarchy. So some more details about how persistent memory works. There are two modes. There is, I will start with the one on the right, memory mode, which is the most transparent. You basically plug in this DIMM. It looks like DRAM, but under the hood, you basically have DRAM as cache, and then persistent memory for the bulk of the data. So the OS boots the system and thinks that it's talking to DRAM, whereas it's actually talking to DRAM as cache and OPTANE as persistent memory. The main goal here is to get cheaper and bigger memory footprints while having something that looks like DRAM. In this mode, by the way, these memory is actually volatile. So if you reboot the system, you actually lose control of this. Right? It just looks like a bigger. It's completely transparent. You don't have to change the application. It just looks like bigger DRAM footprint with slightly different characteristics. The other mode is called app direct mode, and it has a few submodes. But the idea here is that the persistent memory is exposed directly to the OS and directly to the application. There are several things you can do with it. You can have the OS map it to a block device, so it looks like a RAM disk, for example. Or you can actually give access to this thing directly to the application. So the application, if it's smart enough, it can read and write to it. Right? So now the app needs to know whether there's something has to go to DRAM or go to persistent memory. So this gives you a lot more flexibility. It gives you the additional advantage that when you reboot the system, the data is persistent here. It gets deleted here, but it's persistent here. So you essentially have a very fast RAM disk that is non-volatile that you can use for whatever you want. There are a few examples about how this can be used in some database applications, but clearly it sort of opens a whole realm of possibilities. All right, a little bit more about how all the different configurations here. There are multiple ways in which you can see this. So you have on the right-hand side, when you're looking at a hard drive or a SATA drive, you're basically going through an I/O controller to the CPU. The same with an SSD. Fundamentally, it didn't change anything. It's just a faster storage technology, but it's still going through the I/O controller. Now, when you introduce OPTANE, there are three ways in which OPTANE can be used by the system. There is OPTANE that was released last year, which comes in an SSD form factor and also talks to an I/O controller. Or there is the persistent memory OPTANE, which doesn't go through an I/O controller, right? It goes directly to the memory bus. But it can either be go through the file system and driver, so that it looks like a regular, like a RAM disk, or it can go directly give direct access to the application, right? And so this is kind of increasing levels of performance, Of course, you have your DRAM as well with direct access to the app. And so these two are the two modes that I referred in the previous slide. It's a bit of a more complex ecosystem than our traditional memory and storage. Everything kind of merges together. Want to also highlight that there are also, so apart from the persistent memory that comes in this kind of form factor, there is still OPTANE that comes in a SSD form factor, and there was an announcement yesterday as well for the QLC SSDs, which are basically cost optimized. And there is, just to give you an idea, we can put a petabyte, this particular product here, we can put a petabyte in a single U. So it's, we're no longer talking about a petabyte in a single U. We're not talking about a terabyte or 2 or 3 or 4 or 8, but we can actually talking about petabytes in just a tiny form factor. That also makes that the gap between these two getting closer and closer. Okay. So in terms of where can we use something like this? This is a pretty active area of development currently. The data processing pipeline is complex, as you all know. Databases and infrastructure storage and so on. Some of these, the bright blue, are areas where we think persistent memory makes sense, where we can speed things up. And there are active projects about how we can go ahead and do that. Some areas I think are could go both ways, or there are probably use cases which could leverage a slower but bigger system, and other use cases which could go the other way around. All right, so now I'm just going to give a couple of examples. These are solutions that we've developed with partners, and by solution here I mean just it's a reference design where we'll take the software, we'll figure out the best way to configure it, what is the best hardware. And the best and optimize any performance gaps, and show how we can use persistent memory to speed things up or to make things cheaper. Obviously, all these three things are big database companies. This is by no means exhaustive. I think there's a list of like 20 or 25 companies that we've worked with for this launch, but this is just probably the three biggest ones that. Three big ones that are out there that are well known. So for one of the things we did here with SAP HANA was seeing how big a system we could build. So we compared a system that had regular DRAM, which was this. So this is a latest processor. With DRAM only. With DRAM only, we can go only up to, this is with the most expensive DRAM and fully populated DIMMs, we can get up to 6 terabytes system. Because of the higher density of OPTANE, we can do a trade-off, and we can say, let's, instead of populating all 48 DIMMs with DRAM, we can do half and half. So we did 24 DIMMs were populated with 128 gigs, and the other 24 were populated with higher density OPTANE. Result of this is that we have more capacity, so it's a bigger database. We also have a lot cheaper system. There's a big red flag here saying that don't take the pricing as a we're not making any guarantees on pricing, but based on March 1st, a month ago, this is what we were seeing that a system like this is dominated by DRAM cost, and the DRAM cost can be reduced quite significantly. The other side benefit we get from this is the restart time, which goes from 20 minutes to 90 seconds. And that's because the database is residing, for the most part, in persistent memory. And when you reboot the system, the data is still there. You don't have to go and refetch that data. So this is a fairly significant reduction in time. So, yeah, would be nice if I could see the time.
I was wondering where that tab went to.
Yeah. This is a similar experiment we did with Microsoft SQL. These numbers here have to do with comparing a 4-year-old system to a newer system with a whole set of different optimizations, both in the software and hardware. But I'll focus on the right-hand side here. One of the things we can do with larger memory footprint is we can have more SQL VM instances. So we could on the same system we went from 22 to 30 SQL instances, essentially 36% more VMs, and 30% lower cost. And this is a third example with Oracle. We looked at both Oracle database as well as Oracle TIMESTEN. I think some of the more interesting results are here on the right. TIMESTEN is keeping a cache of the overall database. And so two things we observed here. One is so this is before and this is after. With 1.35 terabyte database, it took more than 10 minutes to restart it. With using persistent memory, we can not only increase the size of the database, but now the restart time is nothing. Essentially, it's quasi-instantaneous. Everything is there to start. Another interesting side benefit of using persistent memory is that with the previous configuration, there used to be a buffer in DRAM that after the transactions were committed, it would move it into storage. So with a two-step process. With persistent memory, there's no need for that because the memory itself is persistent, so you don't have to do this commit. So the throughput went up significant, right? So to 6.49. And this is just purely taking advantage of the fact that you're writing to something that looks like DRAM, but is actually persistent storage, so you don't have to worry about the volatility of that system. All right, so I'll change topics a little bit. That was persistent memory. I want to talk about another hardware acceleration mechanism that's new. This is the deep learning boost, also known as VNNI, Vector Neural Network Instruction. And the types of gains that we're seeing are 30x is what is being published, but basically what we're seeing is from the previous generation of this to that. So it's about a 4x gain. And then if you double the number of cores with a higher density core count, you can get up to 30x. And I'll explain what that means in a little bit. VNNI works with a whole number of different deep learning frameworks. It's designed for inferencing, not for training, but inferencing is the bulk of the work out there. And there's work being done for all these frameworks to take advantage of VNNI. All right, so what is VNNI? It is part of the instruction set called AVX512. This is basically a vector instruction. One of the nice things about parallelism is you have, in a CPU, is that you can parallelize based on the number of cores, but even within each core, you have these things called vectors. So if you, instead of using registers, you use vector registers. you can have 112 bits worth of data that's being processed at once. We've had AVX 512 for quite some time, and every year it gets improved with newer instructions. What this instruction does is basically it does a multiply followed by an add. If you think of this as being one vector, so with 8-bit values here, and this being another vector, what this operation does in one go is it will take these two numbers and a constant and come up with that calculation. Just to give you an idea of why it makes the things faster, with previous AVX 512 instructions, we had to do something like this. We had to do the adds and the multiplies separately, whereas this essentially is collapsing multiple instructions in one go. Right? So it makes it a lot easier. And this is the basic instruction in the inferencing loop for neural networks. So it does for convolutional neural networks. So it does provide significant boost. To give you some idea, these were results we looked at with higher end processors. The different frameworks running at different performance improvements. One thing I didn't mention is that Intel DL Boost or VNNI uses int8 as opposed to FP32. There's been a lot of research around this area about how we can basically take a larger number and make it and use a more quantized, smaller number with minimal loss of accuracy. And we took this this idea of doing a better inferencing solution. We created a reference design that should be published by now. It should be in right here. This is the URL for all our select solutions. And we designed a reference design just for AI inferencing, giving fairly reasonable numbers. This is what the solution looks like in terms of hardware. Notice that we're using a gold CPU. This is a mid-range CPU. It's not a high-end. So we're looking at something that's going to be practical and low TCO, not necessarily the highest end performance, but still reasonably good performance. And also, it's not the highest memory configuration, but it does use SSDs and Ethernet and so on. Just the numbers that we saw, and these are actual real numbers for ResNet 50. This is what we're seeing. So we're using two different frameworks, TensorFlow, which everybody knows. OpenVINO can produce equivalent results, but it's better. How would I say? It's better tuned for Intel CPUs. Eventually, TensorFlow, we expect to see similar numbers here as well. But this was an easier to optimize framework for us. And we're seeing higher than 2,000 images per second. We expect that all solution providers will provide at least that use this configuration that we had. This BOM over here, we expect to see that everybody should be able to beat this number over here. And just to give you a sense of how much this improved over the last generation, this is about 3.75x faster than what you could have last week. So when you hear some of these numbers about a GPU being 100 times faster than a CPU, make sure that you check we have the right instruction set and the right framework in place and so on. You will see that these numbers are fairly comparable with a T4 today. And that's all I have. I think one last thought is The software ecosystem is very important here. You can create lots and lots and lots of different exotic hardware that does a lot of cool things, both in terms of acceleration of instructions as well as better I/O, but you need to have the ecosystem work together. There are a number of different initiatives inside of Intel and outside to make that happen. I'm just listing a few things out there, but we need to have, this is a slow kind of progress, right? We need to have the compilers take advantage of the new instruction set. We need to have profiling tools that understand new I/O systems. There is a whole set of things that have to happen. This is really, really important, being able to have optimized libraries that can take advantage of the hardware. Most programmers are not going to go in and figure out the intrinsics in GCC to be able to take advantage of AVX. These things have to be built into libraries so that the end user can see the benefit without having to be an expert programmer. And that's all I have. Just a lot of legalese I need to put here. Not responsible for mistakes and all that kind of stuff. And thank you very much. Oh, yeah. Go ahead, just pull it. Thank you.